Yeah, good morning. I'm Kyungwook Chang from Georgia Tech, and thanks for attending my talk. And today I'm going to present some of my analysis on face-to-face bonded 3D IC. This project is part of SRC project. We collaborate with ARM and Mental Graphics. And let's start. So recently, Intel announced the delayed mass production of 10 nanometer processors, forecasting their arrival for 2019. The 3-year delay from the initial schedule indicates that 2D device scaling is slowly reaching its limit due to these challenges. So the natural question might be what will be the next technology that can follow Moore's law? And how about placing cells in 3D space? So in three-dimensional ICs, wafers are stacked vertically, which makes the 3D IC benefit from short vertical connections instead of using long wires in 2D place. Depending on the size of 3D connections and the wafer stacking direction, we can categorize 3D IC into 3 flavors: TSV-based 3D IC, and the face-to-face bonded 3D IC, and monolithic 3D IC. In TSV-based 3D IC, prefabricated wafers are stacked together, and they are connected with a TSV, which has the largest size among these 3. And face-to-face bonded 3D IC, it is the way prefabricated wafers are stacked on face-to-face manner, and they are connected with the face-to-face bonds. And recently, TSMC announced that wafer-on-wafer silicon wafer stacking technology, which brings this face-to-face bonded 3D IC in reality. In monolithic 3D IC, the transistors are fabricated sequentially, unlike these two. And they are connected with a monolithic interactive vias, whose size is in nanometer scale. And as you can see, the size of the vertical connection is decreasing in this order, so we can achieve higher vertical integration density when we go to this way, but it is harder to actually implement it. There are some challenges in 3D ICs. The first one is EDA tool. So there is no EDA tools which support 3D placement cells. So we need to use some kind of tricks to place cells in the 3D space. And the increasing power density due to the reduced footprint, as well as multiple layers of transistors, makes the heat dissipation complicated, so resulting in higher temperature and requires thermal-aware packaging for 3D IC and the 3D cell placement. To solve the problem with the 3D cell placement, we mimic the vertical connection with a set of anchor cells and dummy wires in this cascade 2D flow. And we implement the 2 tiers, just 2 tiers, simultaneously in a single emulate 2D design, which is called cascade 2D design. And this is an example. In the left figure, it is showing an example monolithic 3D IC. And the right figure, it is showing the corresponding cascade 2D design in EDA tools. So if we cut this cascade 2D design and slide the top partition, then we can actually see they are equivalent. To give more details of the flow, we first partition the functional block into 2 tiers in RTL with the design-aware partitioning, and in the way that it can maximize the timing pass between the 2 tiers. And then we determine the location of the vertical connection in each tier. They should be the same location because they are connected with the vertical vias, and in the way that it can minimize the distance between the functional blocks in different tiers. And in the last step, we will implement the cascade 2D design in EDA tool, determine the XY location and route it. And first, we will put the vertical connection location on top of the empty die with the top and bottom tier area side by side in 2D EDA tools. And then we will connect them with the dummy wires. And then we will put the anchor cells to connect the vertical connection to the, this is M3D design. So this top metal layer of the bottom tier will connect it to the bottom metal layer of the top tier with the MIVs. So this anchor cell will connect this MIV ports to the top metal layer and this MIV ports on the bottom metal layer of the top tier. And then we will make the delay of these anchor cells and dummy wires to be 0. And then we will set the hard fence for the bottom partition and top partition so that bottom tier cells cannot go to the top tier area and the top tier cells cannot go to the bottom tier area. And then we will run normal place and route. Then, because of these sets of anchor cells and dummy wire, it will act as a wormhole to transfer signal from here to there. We can emulate MIVs in a 2D EDA tools. We implement the ARM Cortex-A7 core with the Foundry 28, 14, 16, and predictive 7nm technology. And this die shot shows the 2D and M3D design of Cortex-A7 core in 28nm technology node. And the figure on the right, it is showing the power saving of the M3D design depending on the frequency in 28, 14, 16, and 7nm technology node. You can see the M3D power saving is reaching up to 20%, and also this power saving is increasing as the clock frequency increases. The reasons for the power saving are twofold. The first one is wireless saving. Because we are using short vertical connection instead of long wires in the XY plane, we can achieve wire length saving as shown in this figure. And because of the wire length saving, we can achieve the wire load of each cell is reduced. And we can also reduce the number of buffers in the design, as well as we can utilize lower drive strength cells so that we can achieve standard cell area saving. And it is increasing with the frequency because 2D design is struggling for closing timing with lots of buffers and higher drive strength cells. But in the M3D design, wire load is reduced, so it is easily meet timing. So we can achieve standard cell area more efficiently in a higher clock frequency. With this 3D IC design methodology, we implement the F2F bonded 3D IC for the Cortex-A7 core. And this slide shows the thermal analysis methodology that we are using. We first divide the top tier design and bottom tier design with the squares like this. And structures in each FEOL and BEOL in each square will be mapped to the thermal cube structure. And the thermal conductivity of each cube is calculated with the material composition of the structures in it and also thermal conductivity of the materials. On the other hand, with the cell placement and the cell power consumption, we calculate the volume power of the top and bottom tier active region. And with the calculated volume power, we put them in the cubes that represents the active layer of the bottom tier and top tier. And with this volume power and conductivity map, we run the thermal analysis with the ANSYS Fluent and get the thermal profile. Since this flow is extremely flexible, so we can actually simulate almost all kind of packaging with this kind of flow. Since we just began this thermal analysis So this is very initial version of the assumption that we made for the packaging. So above the silicon die, we have a thermal interface material and the heat spreader and heat sink. And below silicon die, it has a C4 bumps, and the underfill is filled in it, and the PCB model below it. And we ran this is the dimensions and the materials we assumed. And this can be changed. And also, this slide shows the comparison of the thermal profile of the 2D and F2F bonded 3D IC of the Cortex-A7. In the 2D design, in the left figure, it shows the thermal profile of the 2D design in active layer and with the minimum temperature and maximum temperature. And the right figure shows the temperature map of the face-to-face bonded 3D IC at the active layer of the top tier and the bottom tier. Because we can see that actually the temperature of the bottom tier is higher than the top tier, because top tier it is near to the heat sink. The heat can be dissipated much efficiently. But in the bottom tier, heat should go through the PCB layer, which is good channel, but it is less efficient than the heat sinks. So, and also there is a 40-degree higher temperature compared to the 2D design active layer than the F2F bonded 3D ICs. And this is the impact of the frequency on the temperature of the 2D IC and the 3D IC. It is monotonically increased. And as you can see, the slope of increase for the F2F bonded 3D IC is more steeper than the 2D IC. And also beyond the 1.45 gigahertz, it can be in a dangerous region, showing performance degradation or system failure due to the high temperature. And the reason is, it is quite obvious, but in 2D design, the heat generated from the active layer of the design goes to the heat sink and the PCB. But in F2F bonded 3D IC, heat is generated in the top tier as well as the bottom tier. The heat generated from the top tier can go through the heat sink, whereas the heat generated from the bottom tier can go through the PCB. But there is also heat that can trap in the middle of the 3D IC in this area, making the F2F bonded 3D IC has more susceptible to increasing frequency, and also has a higher temperature compared to the 2D design. This slide shows the impact of packaging on F2F design, comparing the if we consider PCB or without considering PCB. Whereas in 2D design, we can see this is the without PCB, considering the PCB, and this is the with PCB. We can see only 5-degree difference, 5-degree temperature difference between these two configurations. But in F2F bonded 3D IC, we can see almost 12-degree temperature difference between these when we are not considering PCB, when we consider the PCB. This graph actually shows in F2F bonded 3D IC, the impact of the packaging is actually larger than the 2D design. So to conclude, and for the future works, we will investigate the impact of packaging more in detail. So we need to find some kind of thermal-aware packaging specifically for the 3D IC, as well as we need to think about how can we solve the trapped heat in the middle of the die with some kind of better power delivery network design or dedicate heat channel, that kind of things. And also, we need to devise some kind of thermal way of self-partitioning so that we can place the power-hungry cells on the top tier so you can use heat sink to dissipate the heat. And also, impact the power delivery network because we will connect the power delivery network to the PCB through the zipper bonds with the TSVs. That will be the good channel for the heat dissipation. And also, we can compare our in-house tools with some kind of ANSYS Redox or Mental Graphics Sahara to compare and make the more accurate our thermal analysis. Yeah. Thank you.
Thank you. Questions? So, do you have any questions?
Yeah. Any question? Yeah.
I'll ask the same question I asked for the first talk.
Yeah.
How did you model the thermal effects? Was it, do you pick an algorithm or a benchmark and you are modeling that? Or are you looking at a variety of algorithms and input data patterns?
Yeah, so we just, in here, what we did is just, for the hardware, we use Cortex-A7, and it can be any benchmarks. We can design any benchmark. And for the, if you are talking about the software, and cell power consumption can be calculated with the software real-world workload, or in here we just use the statistical cell power consumption. So we just assume the switching activity of the flip-flops and inputs, primary input outputs, and with that we calculate the cell power, and we can change that with anything you want. And yeah, that is actually the advantage of our in-house tools. We can configure anything we want, yeah, with these frameworks. Yeah.
Time for another question if you want.
Yeah.
So you said that you used densities of different metals in each one of those blocks to compute your conductivities.
Yeah.
But then how did you weight them when you made that calculation?
So in each cell, let's say the layer M1. So M1 layer. So there is a dielectrics and metal layer. If let's say there is any square that half of them is dielectric and half of them is metal, then we will make the portion of we will calculate the portion of the dielectrics and the metal layer, and using that dielectric and the metal layer, we will calculate the parallel resistive conductivity for the vertical direction, and the series thermal resistivity for the lateral conduction, and use that two resistive thermal resistance to represent the cell conductivity. Is that?
Yeah, that's what I meant. It's a little confusing. I think there's a lot of complexity in terms of how you get the directionality
Yeah.
of the metals, but I can ask you offline about that.
Maybe one last question, short question.
Yeah.
Just one remark. I do believe that going to 3D will help to reduce total wire length, like you introduced just in the first part of the speech, then probably reduce the power contributions of this total wire length, and so on and so on. So how do you, so you compare 2D design, okay, with 3D, and I think that in the 3D design you should have somewhere a power savings to the 3D stack. So how we can see this on your framework? I mean, you just present 2D and then 3D, and there is no power savings going to 3D because of.
Yeah, because of this one, so we can achieve.
There's a power.
Power saving numbers in here.
So when we do 3D simulations in thermal, we should see that there is this power savings, and so the heat should not increase.
Yeah, there is a power saving with 3D ICs, but the problem with so you already mentioned. Let me briefly ask you your question. So, even if you have power saving with the 3D ICs, that power saving might help the temperature of the 3D IC. That is your question.
Yeah, so did
Yeah.
you take the power savings into this?
Yeah,
or did you
we have a power saving with this 3D IC, but actually this trapped heat is kind of unsolvable with this structure. This is baseline and a very initial structure that we assumed. And in this structure, even if the power consumption of the top and bottom tier active layer is lower than 2D design, but the trapped heat is higher because that 20% power saving cannot solve this kind of heat, trapped heat. That increased the maximum temperature of the 3D IC actually. So
That's why I put my solar
yeah, if you want to achieve less heat temperature than the 2D design, we need to, actually, if we increase the power saving, that might be the solution, one of the solutions that we solve the problem, but there can be other solutions with the packaging or, that kind of things.
Okay. That's all the
Yeah.
time we have today. So thank you very much. Please answer anyone.